Today, good morning to all of you. Today will be in the morning half. We'll study on VLSI Analog CAD. Just in the beginning, I'll give an overview of this the CAD activities. That whenever the CAD means whenever we like to design some chip, and to start with the chip, we like to get the fabricated and then see that it is working. So whether it is analog or digital VLSI chip, it goes through these steps. The first is that system specification. In the system specification, we mean that what are the things you want to design. Fine. Suppose you like to design some ADC chip. Okay. So there are various types of ADC. So whether you are needing that, what will be its speed, what will be its number of bits, all this resolution you like to see it. So what is your target of your design, that we specify in the first level, that is the system specification. Fine. Next comes the register level design, which we call it as a functional design. In the functional design, those systems that really what are the blocks it consists of, so those blocks we are to add on, so that comes in the functional design. In the functional design, the next level is the logic design. So suppose we like to make some ALU, we like to make suppose some 8085 microprocessor, fine. It consists of some ALU, registers, timer. So these blocks, again we'll have to design it in the gate level, that we are calling it as the logic design. After that, those gates, again we want to see it in the transistor level. So after the logic design, next comes to that this electronic circuit design. That means we'll break the gates in its transistor level. So transistor level means it will have lot of capacitors, parasitic resistances, parasitic capacitances, everything will have to include in this electronic circuit design. After this design, we'll simulate it, and if we'll find that yes, it is working well, then we'll be moving to the next step, that is the chip layout form. In the chip layout, really we'll try to put that where this transistor will be, where the resistance will be, everything we like to put it in the chip layout form. Then we'll go for this another chip fabrication. Obviously that will be followed by the next step, that is the testing, and if we find that somewhere something wrong, obviously we should go for the debugging, and then we'll have to test the chip. So we need to have this PCB board layout and the prototype testing. Okay, so this is a general LSI, VLSI design steps are followed in the, whether it's analog or digital. But obviously analog thing, this is not really goes by this logic design. So we'll come to this. So the whatever we have said, that can be summarized in this play. See, first we are doing that system specification. Next comes the architecture selection, because lot of architectures are available. So which architecture will be really suitable for your application, that you are to choose it. Then goes the circuit design, that you are to do this circuit design. One thing you will have to remember, that VLSI means it is dealing with million of transistors. As it is dealing with million of transistors, suppose you are doing a C amplifier design, you are finding that after all these your calculations, whatever you have designed, but it is not performing the way you desire. What is the problem? Maybe the resistance you have chosen, it is not really exactly the resistance what you have calculated, or some parasitic values are coming up which is giving problem, but you can do it on the board, you can do some change, and really you can make the things much better. But here there is no chance for debugging. That once you are designing from the very level, that in each and every level you'll have to do the verification. And if the verifier says that yes, you can go to the next step, then only you can proceed. Otherwise, there is a term in VLSI, they call it correctness by construction, that from the beginning till the end, the people go in the step by step, that every level they are thinking, then they are verifying it, whether their thinking process is all right, then they go to the next step, like that they proceed. So first is that architecture selection, then goes the circuit design. You have to do the design, and you can see that each step is again accumulated with this simulation, fine. Then you have to do the layout, and after layout also you have to do this post layout verification, that you have done, you have really gone through all the steps, but still it is not working. So post layout verification is also mandatory. Then IC floor planning, and then packaging. I'll be coming to this point later on, and then prototype testing. The most popular software which is available, one thing you'll have to remember, that human being is having enormous intelligence, but where we lack? Memory. Our memory is really limited, okay? But computer has got a huge memory. So always we like to take the help of these two, that is the human intelligence and computational expertise of computer. If we can combine these two, this gives, that's why you can see that everywhere you'll find it is written as computer aided design, not design automation, because the human intervention in each and every step will be there. Okay, so it is a long history of the SPICE. It has started in 1962 in Stanford and Berkeley. Long story. And after that, the person really who has started it, Peterson, then he switched to AT&T Bell Lab. Then its name has changed from SPICE to P-SPICE, like that. But a lot of people are still working on it, because this is the main tool which gives you the exposure to the really circuit design, and you can do the verification. It has the capability of extracting parameters. So all these things you can accumulate in this SPICE. And as the device, people are changing, the technology is changing, that is, they are accommodating within the SPICE, and that's why newer and newer version of SPICE are coming. So first is the beauty of this SPICE is that it is general purpose circuit program which can calculate and simulate and performance of electrical and electronic circuits. That is the first point. What we can say that it is why we are saying it's a general purpose, that it can calculate, it can simulate any type of circuits. As you know, today there are different technologies that are available, like NMOS, PMOS, CMOS, bipolar, and BiCMOS type of circuit. In Pentium microprocessor, you'll find it's a BiCMOS circuit, because bipolar has a lot of advantages and CMOS has got a lot of advantages. If you can combine these two together, that's the BiCMOS technology, which is available in the Pentium microprocessor. So That's why it is saying that it is a general purpose, that any type of technology, any type of circuit, it has that capability to simulate, fine. And then it performs various analysis of circuits, operating point analysis, time domain response, a small signal frequency response, everything it can do it. As you can remember that when you have done your analog circuit lab, suppose you are designing any small C amplifier, what you did in the beginning? The first thing you did? You have done the DC analysis. So first you'll have to see that whether the bias and all that things are perfect or not. Then you have proceeded, then you have given some signal, and then you have seen how its frequency is responding and all that. So it has that capability, as if it is you are under the virtual lab, you can simulate the whole thing perfectly, okay? And a circuit is described by a file known as a circuit file and must be specified in terms of element names, element values, nodes, variable parameters, sources, and the commands for what to calculate and what to provide as output. That is, I will just give you a demonstration that one circuit you will have to pose your problem to the computer. How you are going to pose your problem to the computer? You will have to give the whole C amplifier circuit to that. So you must give it in the nodal form, that these are the nodes. In this, between these two nodes, one resistance is there, or in between these three nodes, one transistor is there, which one is the ground point. Everything you will have to explain. That's the, once you can explain your program, your problem to the computer, then only it will be able to simulate it. So that your problem, you'll have to pose it to the computer. So that is that you can do it with the SPICE. And one thing you'll have to remember, and you also know it, that is, it should be user friendly. If it is very tough and very difficult to understand, obviously you people will not touch it if anything goes in a very simple manner. So SPICE is very user friendly. The circuit file is the input file to the SPICE program, which produces the output file. How you are giving the problem, that these are the things this is my problem, and now you simulate. So once you give the problem, then SPICE gives you all the output. How it is the procedural steps. That first, the description of the circuit to the SPICE. You will have to describe the circuit, that is, this is my circuit I like to simulate. Then, what are the type of analysis to be performed, whether you like to do the DC analysis, or you like to do the AC analysis, or you like to do transient analysis. All these things you will have to say to him that these are the things I want from you, okay? Define the required output variables, that what are the output variables you are looking for. Suppose this is a very, very small circuit where we don't have any active element, it is only the DC elements. So here you can see that we are giving that 1, 2, 4, 3 node, 4 node, another node is not given, that is actually the ground node, that's the 5. And I'm sure that you know that whenever we are making the incidence matrix, that incidence matrix, we generally prefer here reduced incidence matrix, that the ground point you can just ignore, that which point you have ignored, computer will understand that this is your ground point, fine. So you are to give this element, first you are giving the nodes, then you give the element values, that what are between this 1 and 2, one resistance is there, between 2 and 5, some resistance is there, some circuit elements are there, some voltage source, some current source, all these things you are giving it for the circuit analysis and simulation. So you can see that what are the types of this analysis, output variables, all these things you are giving it to the SPICE, fine. Though it is a video lecture, but I will prefer that if you have any question in between, okay, you can stop me and you can ask me the question, fine. Next comes the circuit analysis. Nodes. Location of an element is identified by the node numbers. I will not go to all those details. Node numbering, whatever we do, computer again renumber those nodes, because you will see that whenever the last slide we have shown to you, it doesn't have any active element. Suppose C amplifier, which is the most simple example, you know it, that one transistor is there. So what SPICE will do it? SPICE understands, suppose between 3 nodes, one transistor is there. What it will do it will take that and it will try to ask you that what is the model of that transistor. Model means it will explain all the voltage source, current source, the capacitances, the resistance, everything, all the detail of the transistor. So once you are breaking the transistor, it is now the network has increased a lot. Okay, so now the passive elements are fine, but active elements you are representing as a transistor. It has its own model parameters. It will transfer it to its equivalent circuit. Once you are translating it to its equivalent circuit form, obviously you can appreciate the number of nodes will increase a lot. And that, so it is the computer's duty to renumber them. And the renumbering of the nodes has its another algorithm, which I will not explain today because of the scarcity of time. There is that whenever we are simulating, what we do with either simultaneous equations we solve, and whenever we do the simultaneous equation solving, that we like to find out the potential profile, field profile, all this stuff, what we do with that, we go for suppose some sort of simultaneous equation solving. There, what is the people generally go by LU factorization. This LU factorization, again, the real matrix in the network, as the network is big, you know, the connectivity between the nodes will become less and less. Suppose there is no connection between 1 and the 99 node or 100 node. So all these portions will remain as 0. So the matrix you will be using, it will become too much sparse in nature. So the sparse matrix you are to deal with, so you should renumber them in a proper manner so that after LU factorization, if the zeros will remain as zeros, so you can neglect those nodes. So that is another big algorithms are available, which we are not going to explain. So when computer is renumbering the nodes, he considers all these points in his program. Okay. As I already said, that node 0 is predefined as the ground. So no node means that's the ground. Node numbers must be integers but need not be sequential, and it is not sequential. All nodes must have DC path to the ground. Okay. So this is the way we just give. Suppose we are giving the previous this, what is the element name, what is the positive node, what is the negative node, what is the value. That's the way you are to describe to the SPICE. Then there are 6 MOSFET models are available. Similarly, BJT models are also there. That MOS1, this model says that square law of IV characteristics. MOS2 gives you the analytical model. MOS3 gives semi-empirical model. MOS4 is the BSEAM model. That's the Berkeley short channel equate model. Then the BSEAM2 is there, because the problem is that, you know, as I'm saying that the still a lot of research is going on this SPICE, because as the technology is shrinking, the short channel effects are becoming more problematic. So the more the smaller is the device, the physics inherent in it is more critical. So those parts people are trying to introduce. If you see, even 90 nanometer technology, the SPICE model, the whole thing, that whatever the model simulation they are doing it, it's not matching with the experimental results. So if you see that IEEE ED 95 paper by Ma, that is giving that 23 fitting parameters, because it is not possible to really translate all the models absolutely in terms of equivalent circuit or mathematical term. So a lot of fitting parameters have to be added. So that's the way people are also changing the models, and they are innovating some new parameters and trying to get more exact results. Okay. I'm just skipping this space. Let us go ahead with the types of analysis. What are the analysis the SPICE can do? First is the DC analysis, which is the first one. Next is the transient analysis. And the third one is the pole zero analysis. You must have done the network, so you understand that pole zero analysis, especially suppose if you do it, you like to design a very, very stable circuit. So pole zero analysis is must, and that actually gives you the stability. Fine. Then the small signal distortion analysis, sensitivity analysis, and AC small signal analysis. And if you are like to be more perfect, you should do the noise analysis. Okay. So all these parts, SPICE helps you. I'm not really going ahead with all this. You can go ahead with this, whatever it's written later on. I'll just come to the layout. Now, it is very interesting to see, no? Some color diagram. This is, if you buy any VLSI book, you will find most of the cover, having some colored strips. These are nothing but, this tells you that which one is the diffusion line, which one is the polysilicon line, which one is the metal, all these things it is said. I just like to say something, starting from the architecture to the fabrication, then all this thing, it cannot be done by a single expert. A lot of experts are involved. They need computer engineer for a good algorithm, good architecture. They need electronics engineers for circuit analysis, logic analysis. They need material scientists for down to the earth, that is processing. So it involves huge number of people. But interestingly, everybody cannot appreciate the problem of others. So to make a good circuit which will be working, the people have designed some DRC, that is the design rule checker. Suppose, can I write it here? See, you are having some MOS transistor. Okay, here is the source, here is the drain. Okay, here is your silicon dioxide, and then on the top you are having, suppose, some polysilicon gate. Now, suppose the length you have kept in between 2 lambda. Lambda, we call it as the design rule. That is the fab lab, they will have some expertise, suppose 5 micron technology or 5 nanometer technology or 10 nanometer. Till today 45 nanometer technology, Intel has gone up to that. So lambda is, we call it as the design, that is the minimum resolution that particular fab lab can do it. Now, whenever you will be making this MOS transistor, suppose the depth is lambda. Okay, here also the depth is lambda. Now, after diffusion, this source and the drain, you will find there will be some lateral diffusion also. As you are putting that diffusion, the depth, there will be some lateral diffusion also. So, when there will be lateral diffusion, the effective length, it is getting reduced. So, if you keep lambda, suppose the distance between source and drain lambda, after lateral diffusion, there is no channel in reality. So, it will not work as a MOS transistor. So, what you will do it? So, that is why the Fab Lab gives you some design rules. We are to follow it blindly until and unless your simulator says yes to the design rule checker, nobody is going to touch your circuit. It may be working very fine, simulation, but after layout, DRC should be through. That means that whatever the design, because the person who is on the architecture level or logic design, he may not be knowing all these problems. So, these design rules comes from the Fab Lab itself. So, we are to follow that Fab Lab's instruction, and we are to accept it, and we are to follow that, and this there is some design rule checkers. Here you can see that, can you just show this? Here you can see it is actually, it is representing one NAND gate. It's a NAND gate. Okay. This green line is the diffusion. Green line, actually it is like a NAND gate is there, one A, one is B, and here it is a depletion mode type of transistor. It is representing this. So, here you can see that this green line is the diffusion line, A, that the rate, it is the polysilicon gate, B is the polysilicon gate, yellow is the ion implantation, and this is the diffusion polysilicon gate, red is the polysilicon gate. So, this color diagram, it is representing one NAND gate. Okay. So, we can see that they will say that suppose design rules like that, that suppose two metal lines are there, you will have to maintain 3 lambda difference between these two metal lines. If you are having suppose this green line correspond to diffusion, here the black portions are the contact. So, this contact between two contacts, at least 2 lambda distance should be there. Like that, lot of design rules are available, and you are to follow them blindly. So, you are, whenever you will be designing your layout, that you will have to consider the DRCs. Fine. Now, after the layout, you will have to find out that the floor planning, that where you will be keeping what. Suppose you are doing some big embedded chip, that there can be some memory unit, some data path, some standard cells. So, all these things together, how you are going to put them, and the floor planning, it is always better to make it in a square form. It is also mathematically proved that if you can put the whole thing in a compact, in a square form, it takes the minimum space. Fine. So, here this is another interesting diagram, that is the power distribution, that you can have like this type of structure. In between you can have some, in between you can suppose in between you can have some chip. Suppose this is your VSS, this is your VDD. You can have some chip here, you can chip somewhere here also. Like this you can put it. So, the power line can be distributed all over this VDD and the VSS part. This is another clock distribution. So, the clock is moving around. Okay, so this clock which is moving around, always you'll have to remember that the clock we are taking care, suppose it is moving from one part to the another. If there will be some delay, then obviously the whatever your simulator, it will not come proper. So the clock distribution is also one of the major issue, that how it can be distributed uniformly all over the chip. Then comes, after your chip is done, chip is fully designed, then it comes what type of packaging you are going to do it, because you should know how many pins are there and what type of different package you are going to have it. Suppose here you can see that in all over the pads, pins are placed. Here is the VDD, here is your VSS, so you can have your core inside. So like that you have to go ahead. So you can have different types of packaging chip, like one is the PGA, you can have the DIP, you can have the PLCC package, you can have the TAB package. So different type of, so where you are going to fabricate, what type of package they will be using, that you should know. Because knowing that the package style, you will have to design your pads. So it is from the beginning to the end. So now I will be trying to summarize that whatever the steps I have said all along. The first is that first point is the determining the specification. You should know that what thing you are going to design. Okay, so specification of that is the first thing you should know. You may be designing some ADC having 250 megahertz but 8-bit. Another thing you are looking for 500 megahertz but 6-bit. So number of bits are different, frequency is different, INL is different, DNL is different. So what are the specification you like to design, that should be known to you. According to the specification, you are to use the architecture, that what architecture you are going to use it. Whenever you will be using some architecture, according to the architecture, you will have to design the building blocks. That what are the building blocks? Building blocks, I do mean that suppose I'll show you one pipeline architecture. There will show that it needs to design some DAC, some ADC to design an ADC. So what are the building blocks to be designed? That to be you are to decide those. Then you are to do the layout of the blocks. So all the blocks you will have to do the layout, and then after doing the layout, you will have to do the design rule check, that whether it is following those design rules or not supplied by the fab lab, that you are to check it. Then after design rule, according to the design rule, you have done the layout. But still there can be something wrong. So you are to do this layout LVS, which is layout versus schematic. You have designed a circuit, transistor circuit. After that, you have translated in its layout form. But when you have translated in its layout form, there you may do something wrong. So LVS takes care of that layout versus schematic, that what schematic you have done it and what layout you have done it, whether it is corresponding to each other, that verification is done in the LVS step. Next come RC extraction. RC extraction is very, very important, because in this, today's state of art, it is not really the delay in the gate it matters. The main delay in the path, that matters a lot. So to extract the path delay, you need to have some RC extraction. So it must be followed by some RC extraction. Next, the post layout simulation. After RC extraction, you are to put those values again in the simulator, you are to resimulate it, and then you are to go ahead with the post layout simulation. So as you understand, it is a $1,000,000 problem, because once you fabricate the chip, by that time you have already spent a lot of money. And if you are not doing correctly, okay, so you can understand what will be your fate. So that's the way. So everywhere in the step, after you design, it must be followed by a simulator which will verify that whether you are on the right track or not. Okay. So the next is the integration of the building blocks to form the entire system schematic level simulation. So now first you have done the architecture, then architecture you have divided into few blocks, then the blocks you have done, you have designed, you have verified. Once they are working well, then you are moving to the next step. You are trying to integrate those blocks. When you are integrating the blocks, that time again you are to do the complete layout, because the connection between those blocks you are to do it. So again you are on the process of layout. So again layout of the complete system you will have to do it. Again the steps 4 to 4E you will have to, again for after this putting all the blocks in a compact manner, you are to do again this design rule checking, layout verification, then RC extraction, post layout simulation. So now the chip is ready. Then you are to find out that estimation of the die area and the number of pins. Suppose you are making such a design which is having the number of pins 50, but the package gives you 48. So obviously that package you cannot manage. So you will have to also estimate, and accordingly you will have to choose the package. So layout of the complete system including the bonding pads. Now there are a lot of questions here. Whenever you are putting the bonding pads are coming as a load. So you may find that some discrepancies have started coming up. So you'll have to again simulate that and again change that. So post layout verification, first you'll have to check the density check, then antenna rule check. That is all the parameters you'll have to extract and you'll have to check them. Then again DRC, that is the design rule checking and the layout verification. So you are moving each small step, you are doing all this verification, then again you are trying to combine, again doing that. That's the way you are trying to reach to the main target. Then you are to go ahead with this selection of the package, then mux layout information for fabrication, that should be with you, and then you can give it for GDS file. Then that GDS file you'll be giving to the fab lab, they will be doing the fabrication. Obviously that should be followed by the prototype testing. Now I will show you a complete design of one pipeline ADC. Suppose you are to design it, it is very much needed for communication purpose. Okay, so for communication ADC you like to design it. See, resolution, first you are to specify, then what is its sampling rate. It is given as 250 to 500 megasamples per second. Then what is its latency? Latency should be less than 10 clock cycles. Then power supply. What is the power supply? You are to specify. Then input signal, that what is the minimum signal, it will be there in the analog input, that is also you are giving it at 0.6 to 1 volt peak to peak, and this frequency you are supplying, that is can be from 0 to 20 megahertz. DNL. DNL is the differential nonlinearity. Do you understand it? Do you understand it? See, whenever you are designing ADC, analog to digital, so what we do it, analog signal, we divide it, 8-bit means we are dividing in 8 bit form. So the signal we are getting it, the whole signal, you are making the signal like this. You are dividing them like this, isn't it? So you know what should be its per bit. It should be 1 by 2 to the power of 8. Suppose you are giving 1 volt. So 1 volt divided by 2 to the power is the each step. But in each step it is not coming exactly the same. Somewhere it is becoming little bit bigger, somewhere it is becoming little bit less. So DNL tells us that in each bit how much nonlinearity has come up. That is, we call it as a DNL, differential nonlinearity. That is, that in each bit how much difference is there. It should be 1 by 2 to the power of 8, but it is not coming. Somewhere it is small, somewhere it is big. So that particular point, that we are giving it as the DNL. That 0.5 LSB, you can accept it. They are giving the specification of that. Plus minus 0.5 LSB means if it will be within that range, it is acceptable to the customer. INL, it says that integral nonlinearity, that is the total nonlinearity within the 8-bit, that integrated nonlinearity is coming. That is how much, that is also is expected. So that is also saying it should not be more or less than 1 LSB. So these are the specification they are looking for, that is SNDR, that should be 50 dB. The process also it is mentioned, it is 0.18 micron CMOS technology, and the power dissipation is also given as it should be less than 200 milliwatt. So this is the specification what the customer has told us that they need this specification. So I'll have to start from this point. So you must remember the very first, it was the system specification. So he has given all the details of the system that ADC I am to design. See here, I'll have to choose a architecture. What do I mean by the architecture? See here, you can see that the resolutions, it is 0, 4, 8, 12, 16, 20 bits are there, and here is the speeds. So if you like to have very high speed, but you are happy with the lower bit, you are happy with the low bit resolution, 4 bit or within less than 8 bit, you can always choose the flash architecture. If it is, you are looking for very high resolution, suppose it is almost 18 bit, 28 bit, suppose you are looking for a better resolution, but you are not bothered about the speed. So that time you can go for serial type of architecture. In between, suppose if you are not that high, you are just looking for 8-bit resolution, but you are looking for little bit higher speed, then you can go for folding interpolating type of architecture. So first, from this graph, you will have to know that which architecture will be suitable for my application, for my specification. If you see your specification, you will find, let me go back to the specification, it is looking for 250 to 500 megasamples per second, that is its sampling rate, resolution is 8-bit. So I can see that, see this pipeline architecture, that the green one, it is suitable. So obviously I can choose this pipeline architecture. So according to your specification, you will have to choose the architecture. After the specification, then comes the architecture. Next comes the comparison of different architectures. It gives you the figure of merit. Figure of merit, see, it involves the resolution, the sampling speed, and the power dissipation. Three things together. Fine. In the specification also resolution was there, speed is there, and power is also mentioned. So knowing that, I can find out the figure of merit. So if you find out the figure of merit you can find by this 2 to the power of n, that is the resolution. Here it is 2 to the power of 8 bit. Then sample is 250 megasamples per second, and power dissipation is 200 milliwatt. So the figure of merit, you can see the pipeline architecture really works well. So from the figure of merit, I can choose that according to my specification, the pipeline architecture is a good one. Now, it is showing a block diagram of a pipeline ADC. Fine. Here, the first, there should be some sample and hold circuit. One sample and hold, then we are having, it's a 8-bit stage, so 8-bit pipeline. So each stage, we are having, each stage has been magnified here. Each stage consists of one sub ADC, one DAC, that is whatever k bits is coming, it is whatever input is coming, it is finding this digital conversion, then analog, it is comparing it, that whatever the difference is coming, again it is multiplied and then giving to the next stage. See, what happens whenever we are making an ADC design, that when we are at the top level, high signal value is high, that time it becomes very easy to tap it and we can translate it into digital form. But 8-bit means one, especially in the lower values, it becomes difficult. So how much resolution you are looking for, and resolution also that DNL you are looking for, it should be less than 0.5 LSP. So here in the pipeline ADC, what they are doing it, that it is first sampling it, that each stage it is finding its digital part, whatever digital is getting, then again it is converting that part to the digital to analog, then it is comparing whatever the first bit coming out, then it is giving to the amplifier, so that whatever remaining part, it is again amplified. Again it is trying to match it, again amplified. So that's the way when it is doing it, you can get a better resolution. So in the pipeline architecture, so after that from each stage you are getting k bits, and then you are having some digital encoder, and that you can take the digital output. It may be a little bit tough for you to understand at this stage, but anyway, see, this is just all the transfer equation in each stage. You can find out that if you know the input and if you know the reference voltage, you can find out what will be the V output 1, V output, all these things, you can find it. I'm just skipping this step. Okay, so now, interestingly, you must have noticed, what was the specification, any of you can remember? It was 250 to 500 megasamples per second. My life will be much simpler if I can get this 500 megasamples and to maintain that power. If I will just like to do it by a single stage or by a single pipeline, life will be much more tough. So what I can do it, I can have this pipelining, parallelism, two pipeline, if I'll put it in a parallel, that one is giving me 250, another one is giving me 250, so I can combine them and I can go for a higher frequency. Even I can go up to 1 gigahertz. That 250, if I have the 4 parallelism and pipelining together, that 4 such a pipeline stage together, I can just go to multiply 250 into 4, I can go up to 1 gigahertz. Okay, so my life will become much simpler. So parallelism and pipelining, always it is better. So far, power consumption is also concerned. For low power circuits, parallelism and pipelining is always sought for. So here, what we have tried to do it, that one pipeline architecture is there, another pipeline, and here you are having some sample and hold. That is, you are going ahead with the 2 stage, and this is, you can do it, the clocking. Okay, so the clocking, you can do it for this blue part, this 180 degree. So you can sample them just by 2 clock, that when this is the first stage, this is coming in the next, that's the using the same clock, you can drive both the things. So if you are using a single clock, that gives you again another interesting, that you can have the less hardware and also the less power. And here, what are the building blocks? We talked that this is the first we have fixed up the architecture from the specification. First, the specification is given to us. From the specification, we try to find out that which architecture for that particular specification will be suitable. We have chosen that parallel pipeline architecture, and that parallel pipeline architecture consists of few blocks, like we need to have a sample and hold amplifier. We'll have to do it. We'll have to use this operational transconductance amplifier, one MDAC, that is that multiplying digital to analog converter, and one comparator. So first, as a building block, I am to design it. So first, I'll have to design the OTA, sample and hold amplifier, then MDAC, and then the comparator. So all these 4 blocks, first you will have to do the simulation. Once you do the simulation, if the simulation is going okay, then you can go ahead with the layout. Once you do the layout, according to the design rule, you are to do the layout. Once you do the layout, then you are to pass it through the DLC, that is the design rule checker. Then you are to go ahead with the LVS, that is the layout verification with the schematic, that the schematic you have used and the layout you have done, whether they are matching, that part should be taken care by the LVS. Then if it is okay, then you can pass it. Then you can integrate those blocks to get the final ADC. This is an interesting diagram of that OTA and the comparator. Here you can see it. We have just shown you some NAND diagram in the beginning, all this colored blue, red, yellow, all these things. And now you can see that your design, your OTA has taken that shape with the colored diagram. Okay, so this is the comparator, and it is also another very interesting thing is there, that when you are doing the layout, ultimately you will be fabricating on silicon, right? So suppose somewhere you are doing more metallizations and all, and some part is vacant, what will be there? There will be mechanical mismatching. So it may break. So in the layout, you will have to think of that also, the stability of that chip, that which part are not used, you will have to take care of them by putting some extra metal so that they remain stable. So in the layout part, it is one of the, when you will do it, you will find it is the most tough part to do this, because other things are done by SPICE. So SPICE does a lot. So after the SPICE's analysis is done, then you can go ahead with this layout. This is the layout of the complete chip consisting of all building blocks. Here is the bonding pads. And very interesting thing, which we have not mentioned, you won't be able to see it. See, even the ground makes the life hell. Analog ground and digital ground. Today, after going back, you just open some ADC from any good company. It is, you can see it even in the internet. Open some very good companies, any ADC chip manual. You'll find VDD analog, VDD digital, VDD, V ground digital, V ground analog. Because this analog ground and digital ground, analog VDD, digital VDD, clock, everywhere they make the life extremely hell. So if you are not very careful about this, that ground also makes, you will have to take care that so that there should not be any interference between the digital part and the analog part. So that's the way you can see it here, that you can just see that analog VDD is there. At the right, at the top, analog VDD is there, and then analog ground is there. Can you see? And then digital VDD is there. Digital ground is there. They are not combined. And another thing, always you try, whenever analog design you'll be doing it, every time you try to use differential mode from the input to the end. Suppose you are giving some clock, make it, because you need it. Any ADC design, you need a lot of digital part, you need also some analog part. So it's not that only analog will be able to do the analog chip. These are basically mixed signal chip. So here, you will have to be very careful from the beginning to the end, try to have all the time a differential type of architecture, which will make your life much more simple, okay? Because so far the noise analysis is also concerned. These are some silicon results which you can do it. They have done it with the OTA, which shows the dynamic range is 1 volt peak to peak. These are the all test results, silicon results of the OTA, which has been shown here. This is the silicon result of the comparator. So one of the technique, this is also just I like to say it, that when we'll be really fabricating some chip, don't go in the beginning that the final block. You will have to make all these building blocks when first you check whether they are functioning well or not. So it should be in 2 steps. The first step, you just design the building blocks, see how they are performing, and then you combine them and see that how those things are doing it. That will be the much better approach than going ahead with the full design. You may find that the things are not really working well. So this is the post layout simulation result of the first stage. You can see that whatever equation is coming, so whether they are matching it with or not, you can check it. This is the digital block of the design ADC. This is the layout of the final ADC chip. First, I have shown you the layout of building blocks like comparator, OTA, these things separately. Now, all the things are being combined, and it is now you could make the final ADC. See, here also you can see that this part are all back end. This part are being taken care These are being done by the metal to take care of the stability, so that the chip doesn't get, um, twisted. So that's the way the layout to be done. So these are the circuit, final circuit, and this layout with the bonding pads you can really go ahead. These are again simulation result, the static characteristics after the chip has been designed. This is also the dynamic characteristics, then the dynamic characteristics. It is, you can see that what was our design? Design was for 8-bit. See, after the testing, this is coming almost to the 6-bit. With so much precautions, but the model parameters could not give you the 8-bit, but it has given you the 6-bit. So this much discrepancies are there from the real design. So that you will be finding it. This is the actually, have you done this SNDR or SFDR on all those? Actually, whenever you are getting some signals, okay, so it is not the 500 megahertz. It will have rather spurious components. So first what you are to do it, you will have to do its Fourier analysis. So what are the components, other frequency components are also available. So that you will have to see it. Suppose you are making 1 megahertz signal. So if you do the second harmonic, then it is going to the 2 megahertz. Suppose you are in the 500 megahertz signal. So spurious signals can come, some 1 gigahertz, 2 gigahertz. And as you are going with the higher frequency, the interconnects problems comes much more. So you'll have to see all of this, that how they are working with all those spurious signals. What are the extra signals are coming? So those things you will have to really check it, so far your things are concerned. So whenever you are, actually I think I have taken a little bit bigger example than what is your, you are very beginner. So, but anyway, you can appreciate that whenever you will be designing anything, that you will also have to do the Fourier analysis of it, and then you are to find out that whatever the things are coming, whatever the other frequency components are coming there, how they are affecting your real chip, those things you will have to check it. And afterwards, when all the things will be done, then you will have to have your PCB design for testing. So without having that PCB design, you cannot, this is the test plan. This has been made on the PCB, okay. This is the PCB has been designed. You can see that we can be proud of our KGP. This is the KGP ADC08, this chip, okay. So it is from Kharagpur. So this is the chip has been, this is the PCB has been designed. This has been fabricated by, we are working for Indian Space Research Organization, ISRO. So for their work, so it may reach to satellite. So that part we are designing, and they have actually this PCB, the whole thing has been designed by them. So then if you test it, and then you can go ahead. So ultimately you will have to come down to the PCB level, whatever the steps we have talked earlier. So those things you are to do it. Sorry. And after that, again we are giving, suppose some ramp response, how it is coming, whatever the other frequencies, whatever the dynamic response, all these things you are to, ultimately this is the summary of the test results. See, the power consumption, it was less than 200 milliwatt, it has come to the 160 milliwatt. So far other things have come properly, but the main thing which didn't come properly, that is the number of bits, because the resolution has really didn't work. Okay, now I'll be appreciating if you ask me some questions, and I'll try to answer if I can. So now I'd like to summarize before winding up, and here you are to help me. Okay, so what should be the first step when you are to design something? Yes, the first thing that I must know what is the system specification, and you will also have to know. Now we have started that somebody has given me the system specification. It may not be the case. Maybe I am designing something. Suppose we are doing biomedical instrumentation. So there we know what we are looking for. So there I must know that which application this ADC is going to work. This specification has been given to us by ISRO because they know where it has its application. So if I'll be designing myself for my own application, I must know where it is going to serve. So system specification should be absolutely, exhaustive. All the things must be there. Fine. So next, after system specification, what will be? Architecture selection. I will have to choose that architecture is, as ADC we have seen that number of beats and frequency. We have shown you one graph, but another thing can come, that is the figure of merit. It is not the speed and the resolution, but some more things are there. That is, today's need is the power. Okay, so you must know the figure of merit also. So the figure of merit will tell you exactly that which architecture you should go for. What will be the next step? No, not circuit design. Which circuit you will be designing? Building blocks. From the architecture you will have to break it to its building blocks form. So each building block you will have to know. Each building block will have its own specification. That is, what are the inputs coming to that building block? What is the output you are expecting? This was not there in that particular specification, but now you know from your, suppose as we have shown you that reference voltages, you will have to choose that what are the inputs for each building block you are looking for and what are the output will be there. That should be, that's for building block specification you will have to design. Fine. Then again you will have to go through the simulation, circuit simulation. After circuit simulation, layout. After circuit simulation says it okay, then you will have to, and circuit simulation also you will have to do like from the DC analysis to the noise analysis. All the steps you will have to do it. After the simulation goes okay, then you are to do the layout. Layout, how you will be doing? What you should know? Design rules. So you must know which fab lab you are going to use it. So fab lab, each fab lab have their own design rules. Here we have fabricated using National Semiconductor. There we are having another lab where we are designing using IHP lab. Another we are having something with the Euro practice lab. So each fab lab have their own design specifications, design rules rather. So you must know that in which fab lab you are going to fabricate. So from there you are to do the design rules, and that layout should pass through the design rule checker. Once this design rule checker is done, then what you are to check? Layout versus schematic. That is that whether layout is matching with the schematic or not. After that, again, you are to do the RC extraction. Find out that you have done the layout, means some lines you have drawn. Suppose two parallel lines are moving. It is working as a transmission line. So you can have some RC. Okay, which can give you a lot of delay in the circuit. That will cause your latency. So latency is also fixed. It has been specified. So you have to extract this RC extraction, and then you have to do the resimulation. And if it works well, then go ahead. Then you have to go ahead with the integrating these blocks. Now after integration of the building blocks, again you have to check the DRCs. Once DRCs are done, then again you have to do the LVS. If LVS is done, then you can be happy and you will be sending it as a GDS2 file to the Fab Lab. Once the Fab Lab is coming, they are returning you the chips. Okay, I forgot this another thing you must know, the bonding pads, that what type of packaging you are going to do it. So whatever the packaging you are doing it, so those package accordingly you will be giving it. So they are going to send you the chip. Once the chip comes, before the chip comes, you will also have to do some PCB layout. That is that PCB where you are going to test pattern, how you are going to test it. So that design must be ready. So whenever chip comes, you assemble them and do the testing. And the testing, it should be also very rigorous. There you should also do all sorts of analysis and try to find out that how it is working. And if it matches, you are through. Otherwise, you'll have to redo it. There is no option. So that's the way you'll have to do it. Is it okay? I was expecting some questions. It's fine? Okay. Another, okay, thank you.